Good morning, everybody. Just making sure it's morning everywhere. It is here on the East Coast, so it is everywhere else that you might be watching right now. Thanks for joining us this morning for this kind of special webinar. We're going to talk a little about LCAT, local climate analysis tool, show some examples. I'm just going to kind of go through and demonstrate. Excited to have a lot of our staff here at the Climate Services branch on with us. Jenna Myers, Chelsea Peters, Misty Furman, Maggie Hurwitz are all on. And we're here to help answer any questions, to take any feedback you have. And with that, we'll get started. Don't be shy about raising your hand and asking questions. Certainly, we'll have plenty of time at the end. But even as you go through, either make a note or stop us if something happens that's unclear. Okay, so let's jump in real quick. So what we're going to start with here, what we're looking at, what you're seeing on the screen now is the LCAT landing page. So when you go to lcat.nws.weather, lcat.nws.weather.gov/home, that pops up. And if you haven't registered already, so you'll see here that I'm logged in. So it says, welcome, Stephen, that's me. But if you haven't registered, you can register there. I believe right now Jenna will get that request and we'll approve your account. So you'll have an email address and a password. That's how you get in. So before I jump in, we'll start with the LCAT itself. That's the tool itself. If you're not familiar with it at all, just a little bit of background. The idea here is that the local climate analysis tool gives you a lot of, it's very powerful in allowing you to do local climate analysis at the station or climate division, or even in the future at gridded data set resolution. And so what we're going to look at today is what our current operational version is of the LCAT. But you should know also that we are actively working with MDL to develop LCAT version 2, which will go into beta testing later this fiscal year and will roll out operationally, hopefully in FY23. That's going to have a much better user interface, although I find this one to be pretty friendly as well, so we'll demonstrate this and go through it if you're not too familiar. But the improved one will have an even better user interface, which will be great. We'll have a lot more variables with respect to extremes that you can do climate analysis with, and we'll also add gridded data sets as well, so you can click and drag over an area to get an area average, instead of having to pick a station or climate division, etc., with some data sets. And like I said, that's going to be rolling out in beta testing mode in the next several months, which is great. And of course, through the VLab Climate Forum, which hopefully you're registered for. If not, I encourage you to register for that forum as well. We send out lots of great information with the climate program. You'll get that information about being able to sign up as a beta tester in the coming months if you're interested. All right, so now, before I jump in LCAT, last little kind of bit of bookkeeping here is Jenna, mostly Jenna, you'll see, if you go into this Learn section, there's a lot of great learning modules. They're not very long. They're going to give you a great overview of what you're looking at, what methodologies are being used, and how you can use it. Okay, so that's really great. I'm going to go through a lot of that here on the demo, but I'm going to have to, just in the interest of time, I'll kind of gloss over things that you might be like, hey, I'm not sure about that. What did that mean? Why are we doing that? What's that methodology? You can get all that information, other resources down here in this Learn section. Okay, so that's what I want to highlight before we jump in. Okay, so with that, we're going to jump into LCAT. We're going to click LCAT. We're going to really pray that this works the whole time. It's usually very, very reliable for me. I tested it last night, again this morning. So we'll jump in here. So when you jump into LCAT, this is your landing screen. And we're going to click on climate impacts up here in the upper left. I'll touch on the correlation studies at the very end, and I'll show you how we can use that. So you jump into climate impacts, okay? And you're going to see, you can pick from multiple different data sets, and then within those data sets, the available variables. So what I'm going to do today, by way of demonstration, is because we just rolled out the winter forecast from the Climate Prediction Center that went out via press release in October, and the updated forecast for December, January, February, meteorological winter was just released this past week, on this Thursday, this past week, on, what would that have been, the 18th, I think? November 18th was the updated forecast that went out. What I want to do is go through some examples of basically ENSO, ENSO and oscillation, more specifically La Nina impacts, and how you can use this in some ways that might help you communicate the winter forecast to your local constituents. And so what I want to do first, as a great resource that you have in LCAT, is to look at seasonal snowfall information and ENSO. So right now we don't have an operational product that's seasonal snowfall. Snowfall can be challenging in a lot of parts of the country, as you might imagine, just like all climate variables are. But what we'll find as we'll go through today is there are some interesting snowfall relationships with ENSO that are robust. And even in some cases, more robust than the individual temperature and precipitation variables themselves. And so as you go through the data set drop down here, you'll see you can do the homogenized station data, which is a good station-based data set, the CPC forecast regions, okay, and the NCIE climate divisions. What we're going to do is we're going to jump down here to the ASIS data. That's the data set that's going to allow us to look at monthly extremes, and it's going to allow us to grab total snowfall. Okay, that's what we're going to look at here, total snowfall. By way of comparison, if you weren't interested in snowfall, you might use the homogenized data, or to get more of a spatial, more representative sample over your CWA or region, you might look at one of the climate division or CPC forecast region data sets, which I'll use later when we look at precip and temperature for the most part. Okay, so we're going to select total snowfall. The first location we're going to do is my hometown, which is Baltimore. So we're going to look at Baltimore Washington International Airport. And the time period, this is a little bit of it's not really a quirk, but it's a little bit of a quirk. In the current LCAT version, you can only look at ENSO relationships with 3-month averages here. And so, and it's going to use as the basis for analysis the 3-month oceanic Nino index, the quantitative value of El Nino during that 3-month period. A new requirement that we just implemented, you'll see in the beta version when it rolls out, the new period, is that in the new LCAT version that rolls out, you're not going to be constrained to a 3-month period. You can actually look at a 3, 4, 5, or 6-month period based on that first 3-month average. And the reason that's going to be useful, I think, is for a lot of offices and stakeholders especially on the West Coast, but all over the United States, where the water year is important, where you want to look at up to a 6-month average. Using the original ENSO value as the basis, which is scientifically sound because ENSO operates at longer timescales and with a lag, right? So that's going to be important. Less than 3 months, and then once you get beyond 3 months, like for a whole, for a calendar year or something, using a single ENSO value is not going to be as useful and more prone to misinterpretation, misapplication. But that 3 to 6 month window is really useful and sound for using ENSO. So that's something that we'll be able to do in a future demonstration. Here you can set the time. We're going to do 1950 to the present, or 2020, because I'm going to use DJF, which is meteorological winter, which it goes through. This is December 2020 through February 2021, this past February. So that's what we're looking at here. The first thing we're going to do in Baltimore is you can look at these drop downs. You can either add a climate change analysis, which I'll show you how we'll do that in a second. But first, we're just going to do a climate variability analysis. Now, when you go into climate variability, you can look at a few different options. So if you select the 3-month period now, or in the future version, a 3 to 6 month period, you'll see the ONI, or the Oceanic Nino Index. That's the El Nino Southern Oscillation time series that we utilize. You'll see the Arctic Oscillation, the North Atlantic Oscillation, the Pacific North America pattern. The first one, the reason ENSO is so powerful is that it's most useful in a predictive capacity, and that's because it has a very low frequency timescale, and it's a very known physical forcing mechanism. So if we think of the tropics and extratropics as kind of separate entities, which they're not, but to refer to a kind of zero first order, you can think of the tropics as on ENSO timescales. ENSO is a forcing mechanism for the extratropics. So we can think of the result we're seeing is very much forced variability. And that's why it serves as the basis of seasonal prediction. You can go through and use the other ones as well. And what you'll see there is it'll give you a really good understanding of using ENSO as saying this is kind of the predictable component of the variability, and the other patterns are less predictable, or at least on seasonal timescales. And you'll see that LCAT's fundamentally monthly data. One thing that is interesting and noteworthy is that we are in the climate field working on, especially with AO and NAO, looking at seasonal prediction. That's certainly something that I would imagine we'll be able to say something more about over the coming years. So we'll click ONI, and as you go down here, you for ONI, you always, the critical values that are used for the analysis, the thresholds, are minus 0.5 and positive 0.5. That's the operational definition of El Nino to the right of 0.5, and La Nina to the left of negative 0.5, and then neutrals in the middle. So that's what we'll do. We'll click local ENSO impacts. These are kind of the traditional composites. So we're going to take all of the El Nino cases, all the neutral cases, all La Nina cases, and we're going to count how many times they fall above or below normal. I'd like to do 2 category analysis. You can do 3. That you can, play with that as you will. The other nice thing that you can do in LCAT is you can pick a climatological reference period, or you can pick data percentile. The data percentile is useful because, in this case I'll show you, is that because it picks as the median, it picks all the data going back in your entire period of analysis. So we pick the median value, and now we're going to count how many times the seasonal snowfall falls above or below that. All right, so with that, we'll click Analyze. We'll hope we get no errors, which I think we won't here. And we'll see the results that I'll go through here in a second. Here we go. Perfect. All right, so here's the December, January, February time series of snowfall. So for those in the Eastern Conus or who have love of winter weather and big seasons, you'll see some of the big seasons poking out here. This is 95, 96, which, as you'll see, is our La Nina outlier. You had the 2002-3 El Nino and the 9-10 El Nino poked out here. And then this little peak here is the 15-16 El Nino, which had, of course, the big East Coast snowstorm in January of that year. So you'll probably see where we're going with this. What's nice about LCAT also is you put a time series, and then with each graph, there's an interpretation statement. And so this tells you what you're looking at, okay? And this is really powerful, well vetted. It's formulaic, of course, and so let us know if you have any questions, concerns, or need help understanding what this is saying. We'll be happy to help you out. So you go to the next one. This shows your basic histogram. This gives you an idea. You can eyeball this, and you can get a feel for whether or not the data is normally distributed. And so it uses these statistical values of things like skew. Oh, sorry. It gives you these statistical values of skewness and kurtosis up here. And for those of us, with stats, right, if you a normal distribution, you're looking for something that looks kind of like a bell curve. This, of course, does not look like a bell curve. Not surprisingly, a lot of precipitation and associated variables like snowfall are non-Gaussian. And in this situation, it does in fact tell us that we would need to reject the null hypothesis in favor of the alternative. So what this means is that this is most likely not normal distribution, okay? But it gives you a nice at a glance. This gives you a breakdown relative to the reference period. Now, what I picked for the reference period was I picked 1950 to 2020, and I picked the 50th percentile. So this should turn out at 50-50 by definition. Now, because of some rounding error, what we select as a median, because in snowfall you have some values close, you might get a couple, tenths of a percent on either side, but that should turn out roughly 50%. And in the next box, this is the essence of the composite analysis. So in this box, in this graphic, you see you see the La Nina on the left, El Nino on the right, neutral in the middle, and you're looking at the frequency distribution. And so what you see is in these the boxes with the bold outlines indicate that result, that difference, is statistically significant at least a 90% confidence level. And of course, there's an associated statement, interpretation statement. Now, if we scroll down a little bit, you get all the way to this significance level table. And this is really the meat and potatoes of it. This highlights a really nice, fairly linear relationship between ENSO and snowfall at Baltimore. And so if you look at this, you see that for La Nina, you have actually the most significant signal below normal snowfall. Below median snowfall is favored 99% of the time. And then during El Nino, 72% of the time, it's 99% significant. And then you get a 60-40 split with El Nino, and that's significant at about 92% confidence level. And then in the neutral bin, you don't have a significant shift. So that makes sense. So that means that you don't expect that ENSO has a fairly linear relationship here. I see we have a question. Let's see what we got here. Great question. So Kyle asked, will the new climate normals period be updated? So that's a great question. I do not believe we're going to update it in the current version. It's in the new version that's going to be rolling out for beta testing soon. So the new version already has the 91 to 2020 normals period in it, and that's going to be rolling out in the new version soon. That's a good question, one that we get quite a bit. That being said, I'll just say that having the base period itself is nice, but it's not essential to drawing some of the conclusions that we're going to draw today, or that you can draw in general. So all base periods are doing is giving you a basis for analysis. It can actually be kind of clunky sometimes when you have a lot of trends, and that's why I'm sticking to the 50th percentile analysis here. But I'm going to show you some examples where we'll see trends. Okay, so all right, so we look at that. So this is great. I think it's a very powerful result, right? So you can look at, you can say, so in the mid-Atlantic, roughly, Baltimore, Washington area, there's a significant relationship between the El Nino Southern Oscillation and snowfall, accumulated snowfall during the December, January, February period. Now, what's interesting, and we'll say, we'll leave this as an exercise to the student. Another good question came in by Victor. I'll address that in a second. One of the things that you'll see if you go up the East Coast through Philadelphia, New York, Boston, you'll see this relationship breaks down. And so that actually this ENSO relationship is less important as you go northeast, but it does maintain itself as you go southwest. So I'll show Roanoke next as another good site example. So Victor's question was, okay, so we do this, can we break it down by weak, moderate, strong? So right now the answer is no. Now, why would we do that? So the reason we do that, and we probably could revisit this pretty soon, but basically what happens is, as we get away from the bulk analysis, I'll show where are we? I'm looking for the number of events here. Let's see if I can find. So this gives you the actual negative phase list, neutral, etc. That's okay. Oh, here it is. This is what I'm looking for. Number of events. So you have 71 total years, and they're split roughly a third each. Okay. What happens is, as you start to slice the bologna a little thinner and thinner, your sample size goes smaller and smaller and smaller, and so your threshold for significance goes up, and it becomes difficult to draw the same statistically robust interpretation of the results. That being said, we are getting more and more years, right? When this was developed 10 years ago or so, I guess not quite that far, but pretty close, 5-10 years in the planning stages, we had 5-10 years less data. So as we get more and more data, it is going to be important for us to revisit the ability, basically, to move these values, okay, to Victor's point, to let you move those thresholds. So instead of minus 0.5, you do plus 0.5. The reason it's fixed at 0.5 is because of this concern that we're going to be slicing bologna too thin and kind of, quote, finding results that might not be real. However, what you can do is these data percentiles, you can change that. So actually, let's do this. So we can make this, let's say we make this the 90th percentile. Okay? And so this is going to be how many times, what effect does ENSO have on exceeding the 90th percentile? So that's, again, slicing the bologna a little thin. We'll see what the stats tell us. So this is a real-time test. So of course, time series looks the same. It's the same data. We're just looking at a different level. So here we see a 90-10 split, because that's what I told the data to give us overall. The next one's going to tell us what we have. Oh, here's a perfect case, okay? So in this situation, you see what you expect, okay? Which is that the chance of being below normal is higher in La Nina than El Nino. But what happened? Well, so in negative phase, there's 22 events. What's 1 out of 22, 4.5%? That's 95, 96. So what happens is the single winter, 1995, 95, 96, because it was a top 10% snowy winter, blows up the whole analysis effectively and basically makes you not able to draw a conclusion at this tail level. And so that's why the larger you keep data samples, this is what you see in the tails when you do a tail analysis effectively. But if we go down to like 75, my hypothesis is that 75 will be able to retain the signal. So let's see. So hopefully you see what my point is that as you constrain things in either the predictor or the predictand, you become very sensitive to these outliers, and it makes it harder and harder to draw the same conclusions. I.e. that the tails get trickier. Perfect. So here you jump into the 75th percentile, and now your relationship is now significant again. Okay, and it's significant at these very high levels. Okay, so you can do that across the board. You can see, how much can we kind of bend it? How far can we push it and still draw a robust conclusion from it? And so in this example, right, you can draw this conclusion. It's very robust up through the upper quartile even. Okay, so that's a little bit more of a advanced usage or ways we could consider it, but definitely an interesting application. So thanks for the question. Longer answer is yes, we need to revisit these critical thresholds in the future. But you can do it on the other side right now. You can look at, you don't have just to look at terciles or 50th percentile. You can push the envelope, so to speak, into the quartiles, quintiles, etc. Okay. I see Brian has a question. Yeah, so Brian, if the 3-month periods are grayed out, it probably means your end year is 2021 instead of 2020. So if it's 2021, some of those periods are going to be grayed out at the bottom. Yeah. Good point. All right, good question. Okay, great. So I want to show a couple other things that you can do here. Time's flying by. Okay. So one thing that you can do in you can also just do a departure from normal analysis. Let me show this. Because the departure from normal analysis just tells you basically the classic composite. What's your analysis look like in terms of, what's your anomaly during these periods? Actually, let me set this back to 50. Close enough. I think it doesn't matter for this analysis, but it might. But in any case, you see La Nina is below normal, neutral slightly below normal, El Nino is above normal. Now that's also weighted by there's slightly more El Nino events than other ones. That's how we get the anomalies to sum to 0. Here we go. Yes. So same answer. And so this is just our mean value of the whole period is 16. During La Nina, you tend to have less than that. During El Nino, you tend to have more than that. The last piece of analysis that I think is really powerful visually are the box plots. This is very similar to data you can actually find on the CPC webpage, but this extends that into snowfall, seasonal snowfall. So this can be pretty powerful. So we'll wait for this to load. Here we go, perfect. So data is all the same, no surprises. Jump into the box plot. So here's the box plot, and I think this is really nice. I think I showed this on a call I did pretty recently. I think it was a teleconnections webinar, just showing an ENSO example. I think I was showing this exact box plot. And so what you see is the medians go up from La Nina to El Nino. The upper, the 90, this is probably I'm not sure if this is the extreme or no, this is probably the 90th percentile. And that goes up with each, as you go from La Nina to El Nino, and even the 10th percentile kind of creeps up. And so what you see there is a really nice signal in snowfall there. So that's that. I do want to show how you can use trends. So the hinge trend is something we use to fix a flat line through 1975 and then a linear fit from there to the end. And so when you detrend based on that, and I'll show another example of this in a little bit, it shows you essentially how trends are affecting your composite analysis. So in areas with strong trends, I'm going to show a great example in Northern Alaska, because that's the most obvious example of this, where your trends are strong, they overwhelm the actual variability signal, so you have to account for that. What's fascinating is in Baltimore snowfall, there's almost exactly 0 trend. Right, so there's a hinge here in 1975, but you can't tell because it's just flat. So in this case, you can say, well, there's no trend. We don't have to worry about it. We can just deal with the variability. Okay. So the other example I want to show though is Roanoke. And so we'll just do Roanoke International Airport. We'll do the same analysis, same exact analysis. I'll do the hinge, I'll detrend it, I'll show you what that's going to do. We'll do the standard composite. We're going to do the 50th percentile, and we're going to run it. So Roanoke's a little farther southwest, kind of in the mid-Atlantic region. Let's see, got another question coming in. Time flying. Awesome. So, let's see, where are we? Perfect. All right, so here, what happened? Meshes is. Let me just do it again. I'm confused. I confused myself. I've tested this a lot. This is fine. So this is. Let's make sure I put it in what I thought I was putting in here. Oh, here we go. Okay, so here's Roanoke, and so you see the El Nino case is just below the significance threshold, and but the La Nina case is still significant. And then when you get into different methods of detrending, you can do hinge or OCN. Sometimes when you detrend, if the signal gets weaker, that's interesting, and you expect the signal to get stronger sometimes, but if it gets weaker, it suggests that some of the signal might actually just be kind of an aliasing of trends in ENSO. But also it can be, and I'll show an example of this in South Florida, when there's a pattern of clearament variability that explains a decent amount of variance, depending on the type of trend you use, that you can actually end up removing the signal itself. And OCN 15 is an example of that. Okay, here's a great example. So here, when you remove the OCN, so you remove the running 15-year mean from the data, which is what this is doing, and here then you reveal a strong, really linear, nice-looking linear fit. Now, if you go down to the box plot, you do this. So this is the box plot. You can see this pop up here. Here we go. Good. And you see that very nice characteristic change there from below normal during La Nina to above normal in El Nino. Okay, so I think that's a good example. I want to show one other snowfall example. I was going to show like Minneapolis, Detroit, parts of the upper Midwest and the northern plains. You have the opposite relationship. You'll see some significant increase in snowfall during La Nina years and decrease in El Nino years. But there are some instances where they're less linear and potentially interesting. And so the one example I want to show, and you might see this in some places out west, is I'll look at Albuquerque. This was an example I looked at in Albuquerque. So let's take a look here. We'll just do 50th. Let's see if it'll reset for me. There we go. This one I set at 50%. And if I remember correctly, this is one of those stations where there's not much of a signal during La Nina, but you get a nonlinearity. And so here, first of all, you can see there's not a particularly large trend, but we can take a look at it. And then boom, here you go. So this is nice. So what happens here, this is kind of interesting, is you have a really strong signal during El Nino. Okay, so El Nino definitely favors above normal snowfall. But then what happens is below normal snowfall gets kind of shoved, so to speak, into the neutral and La Nina categories. And so what you can see this really nice in the box plot. And I'll show here. Perfect. Okay. So you look at the box plot, you see during El Nino, there's a clear shift from the other two. And so that's kind of interesting. Typically, non-linear signals like this make us a little uncomfortable. But there's 71 years of data. There's probably something real here. And so you can kind of rule out those as being, yeah. So I'm looking at a question. So you kind of rule out, for instance, in the case of Albuquerque, not ruling out's not the right word, of course, but you can say that, well, during El Nino years is when you tend to get a lot more of your snowier winters during December, January, February than later. And of course, you can do this analysis through all the seasons. So as you go out to the Intermountain West, parts of the West, for instance, the snow seasons tend to be a little more bifurcated, not centered in DJF, so you can kind of shift it. And that's one of the reasons the new LCAT expanding the ability to do the analysis over like November through April will be very powerful. So we're looking forward to being able to add that and look at this type of analysis in that framework. So let me do, to Kyle's question, yeah. So what's happening in the data, ThreadX stations are not in here, Van. Someone could jump in who knows data better than I do. I'm more of an analysis junkie than the data junkie itself. The relationship between ThreadX here and the other data. So we have ACES, and I believe these are all the same. From the ACES data, we have a much larger pool of variables in the new version that you'll see that rolls out. In terms of specific variables that are in ThreadX that are, I guess, is it the stations that are different? I'm not sure. I'm going to have to defer to one of our data analysis experts, our data experts who can kind of help me with that. So Kyle, what happens in data in percentiles? Yeah, go ahead. Thanks,
this is Jenna. Jim would probably answer that better, but I believe there is a reason why we have ThreadX not in here, and it may be because of the fact that it's not a homogenized data set, or I don't know. I know that there's specific reasons why we have the data that we have, because they're filled in or extrapolated or whatever.
Yeah. I saw Chris. I just unmuted you, Chris. Stachelsky.
Yeah, so I think part of the reason it's not in there, I mean, first of all, they're going to be separate stations under separate GHCN IDs. So that's part of the issue. But the other reason is I would agree with what Jenna said. It probably has to do with the homogenization. I mean, you have some sites that are not really compatible moves. They're more than 5 miles in distance. Some of them are like, 8, 10. Like Pittsburgh is an example. I mean, the airport is like 20 miles west of downtown. And the older records in Pittsburgh prior to like 1950 were kept downtown. That's almost, we wouldn't even really consider that a climatologically compatible move. And so in some cases, you may even see trends in the data with sites that ran, warmer, colder, wetter, drier, just based on the location of the station that have absolutely nothing to do with ENSO or any of these other variables. And in some cases, that could skew your results or bias them probably worse than anything else. So you're much better off picking an actual point that hasn't moved. It's a much cleaner, data record. But but the main point, you're right. If you want it for ThreadX, there could be anywhere from 2 to 5 or 6 sites that are separate GHCN IDs in there. And also for some of those ThreadX sites at one time, NCI did not have all the data in GHCN 10 years ago when this was rolled out. That would have been another problem. So.
Great, thank you, Chris and Jenna. So I'll jump down to the percentiles question here real quick. So what I just redid the Roanoke analysis using the climatological terciles. And what you see here is not the problem, but one of the things you'll see when you do the climatological terciles, which is that because the climate's not stationary, you go all the way back from 1950 to the present. What this means is that there was more above tercile, above the 81 to 2010 tercile events in the whole period than 33%. And so because the climatology doesn't even come out a third, this by itself is just telling you there's been some decreasing trend in Roanoke. And when you remove that trend, depending on how you remove that trend, you might see a more or less significant signal. And so here it's retained in El Nino, but less so in La Nina. So you still see the quote shift towards dry, but it's just not as significant. And then this shows the other quote weakness a little bit, is that again, as you go into terciles, you're now slicing data more thin. So anyway, when you go into the percentiles, what the percentiles are now doing is basically ignores this reference period, or you can do it here also. But I like to do 2 category just because it makes it nice and simple, big sample sizes. So it defaults to 50. I had moved it to 90, and then you can slide it back. It's just taking now the whole data. So you have 71 cases, and it's taking the 36th value as the median, and now it's counting how many are above that and how many are below that. That's it. So it's a nice way of not that you don't care about trends, but I'll show you an example where you still care about trends, but where you get an analysis that to your eyeball, instead of having to, so when I'm eyeballing this, okay, I see these are bold, but like they're all favoring above. Why is, like, what does that mean? It's because of the trends in the data. And so I think it's visually easier to use the percentiles, but that's just a preference. The data is all the same. It's just how we're kind of slicing it to interpret, and then what interpretation we're drawing from it. And so you'll see a lot of those good references, good examples in Jenna's talk about, in Jenna's materials about how you can, in the learn section, about how you can use these and interpret them. So that's a good one. Now, I want to show an example. I'm going to jump into, we can do homogenized station data. And we'll do total precip. So you can see in homogenized station data, we don't have snowfall anymore, right? So we have to use that. We're going to go down to Miami because that is a really nice. We'll do Miami International Airport. This is a kind of your classic precip signal for El Nino and La Nina. So same period. I'm not going to add any trends quite yet, and we're just going to look at the ONI. We're going to look at the split, and we're going to see something that's really strong. Well, we should, right? If we don't, something's wrong, right? Okay. So again, the climate is the split. Depends how the software interprets the actual median, right? That's how it determines whether it gets tossed the rounding thing, whether it gets tossed in the above or below. And then here you go. This is classic, right? Nice linear signal, wet El Nino, dry La Nina, and neutral 50-50. Okay, and look at these. Look at these bad boys. 99.8, 99.6 significance. So this is what we'll call a no-brainer. That's why if you look at our forecast maps from the Weather Service for DJF, it's dry in South Florida, right? That's just what it looks like. Now, I want to show an interesting example. So suppose we want to get cute, and with precip, we want to remove the 15-year OCN, okay? And so so what's going to happen is I'm going to detrend the data using the 15-year running average, okay? And this just has an interesting result on the significance that I just want to show you. Okay, so you still see the significant result, but it's not as significant, which is kind of interesting, right? So it actually becomes less significant. The signal is weaker, slightly weaker when you remove the OCN. That's not real. It doesn't mean that the signal is actually weaker when you remove the trend. It's because ENSO is such a dominant driver of year-to-year variability that because ENSO isn't evenly distributed between 15-year periods, a good portion of that trend is just the random allocation of El Nino and La Nina years. And so the cautionary tale that I'm providing here is that when you see a really strong signal, just without detrending anything, then you're going to have to be concerned that when you start doing trend analysis and trend removal, things can get a little murky because you might be removing the signal that you don't think you are. And this is the best example that I just found easily. So again, usually you'll still see the signals that exist. Those will be a little bit weaker. So what's another great place? And then we're going to jump into the CPC forecast regions, give us a little bit broader area. This only has temperature and precip. So we'll look at total precip, and we're going to go to a favorite place from thinking and debating ENSO impacts, which is Southern California. So California, Southern California coast, CPC region 93. Again, we have to go back to the 3-month average here. We're not going to detrend anything right away. All right, and so we have our standard setup here, and we're going to click Analyze, and we'll see what happens. Generally speaking, for detrending, we prefer hinge for temperature, temperature-related variables, and OCN for precip-related variables. But again, there are applications where you could justify a hinge trend as well. Off the bat, eyeballing this, there's not a huge trend here, but I'll show something that's interesting in a second. So we go through this again, just the climatology even split, and now here you go. This is pretty neat. So what are we looking at here? We're seeing that there's a big increase in the probability of wetter than normal conditions during El Nino, but it's less linear. And so what you see is that the driest signal actually ends up in neutral years with a dry but weak signal in La Nina years. So again, that's kind of interesting. You can see this if you look at the box plot again. The box plot will show this. But I have an interesting trend analysis on top of this that I think would be interesting. So again, same data, nothing new, and then the box plot. You see something similar to what we saw with Albuquerque's snowfall. Okay, and that's this here. What's interesting is that in this analysis, there's enough neutral cases that are low that it doesn't trigger this, that it triggers a significance even before the La Nina does. Now, what I want to show here is now if I remove the OCN 15, so we have a signal. There's definitely an ENSO signal. It's not nearly as strong as South Florida, but it's pretty robust. So I'm going to do an OCN 15, and now I'm going to remove that. And we'll see what happens here. I didn't mean to do box plot, but we'll look at the box plot because it still plots the change data. And now we have a little bit more of a linear signal. So the La Nina is actually lower than neutral. So when I plot the actual composites and the associated significance, the composites are the most powerful quantitatively because it quantifies the significance of the relationship we're looking at. And so that can be very helpful.
Hey, Steve, can I jump in real quick again? You can just do like a functional thing when you're selecting the menus, you can select one or more of those items on the analysis.
Yes, you can. Thank you. Sorry. That's actually a great point, Jenna. I'm just being a little sloppy, but you're absolutely right. So you can actually just hold Control or Shift, I think, select them all, which is what I probably should have done the first several times I showed you. I just got in the mood of doing it. But yes, you can also select more than one trend. I don't want to get into how you would use that here because you can do ensemble things. But here we go. Oh, I did a hinge at OCN. That's why I messed up. All right, perfect. Sorry, because again, a hinge isn't really always great for precip. And because there isn't much of a hinge trend, you get the same values. But the one thing I wanted to show that was kind of interesting is that when you remove the OCN 15, instead of the trend, the linear trend, what you see is actually this more significant signal across all of them now. And that's the associated box plot I showed. And so now you see this, which is really interesting. So you see a really good El Nino signal, and then that kind of gets sent evenly into the neutral and La Nina years. So what does this mean? What this suggests is, in this case, that relative to the decadal state you're in, it suggests that there's decadal variability at play in the data set. That when I remove the decadal signal, which is kind of what OCN 15 is doing, you see an even more robust ENSO signal. And so that means that ENSO has an impact in Southern California, but it has an even larger impact in the context of the current decadal state, if that makes sense. So that's kind of one of the interesting things you can do there. All right, let me transition. I'm going to show some really where trends are absolutely essential. So let's jump up into Alaska. And for this, we're going to go into the station data. We're going to look at temperature, and we're going to go to, it's still called Barrow in this analysis and this framework, but I believe it's Ukikvik in most of our other things now. So if we do this analysis here, I'm not going to show any, we're not doing any trends yet, but we're going to show just the ENSO analysis without any detrending. Okay. And so this shows you where you'll see. sometimes you have to detrend or else the analysis doesn't make sense. So here you can see there's a nice pretty linear trend here. The data is nice and normal, which is nice. Again, it's split roughly 50-50 because that's what I told it to do. And you see, not really much of a relationship, right? Maybe a smidge warm, but nothing significant. You can see down here, nothing statistically significant. Look at our box plot, nothing going on. So you can say, hey, there's no relationship in Northern Alaska between temperature and ENSO. And I'd say, well, no, not quite. So this one you can do either. I'll do an OCN 15. We'll detrend based on that, and then we'll see what happens with our analysis. And then I'll kind of give an explainer of what happened, why. Here we go. So here's the OCN, and then when we remove it, the red dotted line is now our detrended data set. So you would expect it to not have very many trends. So it looks the same, it's distributed the same, and now we see a statistically significant relationship, especially during La Nina, where it favors cold. And then you do see a shift in El Nino, but it's just stronger. But you actually see this neutral favoring above normal. And then our box plot here, where you can now see La Nina favoring cold. Now, so why is this important? Well, here's a case where you have significant trends in the data that prevent you from seeing the ENSO signal. So if you're in analysis over, if you're analyzing over an area like Northern Alaska, or even over the CONUS, you can show similar things in like the Southwest CONUS during certain seasons, where the trend is by far the dominant pattern of variability you see in analysis. That will obscure your ENSO signal. You have to detrend. So I've done this also farther south, like over Anchorage. You see something similar, but it's not as dramatic. The trends over Northern Alaska are much more dramatic. So I see another great question by Brian. So yes, right now ONI analysis only works for periods for 3 months. We're in the updated version, the version 2 that we're going to roll out in beta format in the coming months. That's been changed so you can select a 3, 4, 5, or 6 month period, all using the 3-month ONI from the first season. So for example, instead of having to do DJF, I could do a 6-month period from November to April. It would use the November, December, January ONI as the basis for analysis, but the target variables would be the 6-month average. And so that's going to give you a better idea of whole season, cold season, water year type analyses. As you get longer than that, the problem is now there's questions about which ENSO should I use, and is that the driver? So 3 to 6 months is kind of a sweet spot for looking at ENSO, for looking at a single ENSO value, right? So if I take this, the current OND ENSO, that's a really good October through March predictor. Okay, if I start drifting too much farther down into next summer, I'm just going to muddy the data analysis. So that will be an improvement that you're going to see in the coming version, is that you can do that. Exactly, Brian. Exactly, because winter's longer than, so you're going to be able to look. You're going to be able to look at your winter season, use the ONI from the first half of that winter season effectively, and then you can see that relationship over the whole period. Exactly, and especially areas in the West will be just as effective. Yep, great point. All right, so let me leave it there. Those are the main things I wanted to touch on. Showing how you can use ENSO and snowfall relationships to add value to winter forecasts coming out now, help you communicate it. And then also when you look at ENSO and precip, ENSO and temperature, that also helps you add context to the official forecasts that we're publishing. So for instance, if you see something that's different, so a great example is where trends and El Nino and La Nina are counteracting each other. So here's a great example, and I honestly don't know what this looks like. So let's do this in real time. So I'm going to jump over. I'm going to look at attend audience to make sure you see what I'm seeing when I do this. So I'm going to go to the right now. Boom. Yeah, here it is. So here's the latest outlook that came out, 3-month outlook. December, January, February. Here we go. This is a great example, even better than I hoped. So if you look at Alaska, look at this. We have equal chances over Northern Alaska. Well, what's happening here? We just saw La Nina should give us like a 70% chance plus of below median. And I know that's not below tercile, but it should give us a signal. Why is it equal chances? Well, because we saw the counteracting balance, which is the trend. So if you look at it without detrending, you basically see no signal, and that's where you get equal chances from. Because what happens is the trend would give you a positive anomaly. La Nina gives you a negative anomaly, and those kind of cancel out. In a future world, that might even mean we favor like near normal, but that's a little bit beyond where we are right now. But that's why, and that can help you explain that, right? So if you're talking to stakeholders in Northern Alaska, not to pick on Alaska, which is a good case, where you look at it and say, well, that's odd. We know La Nina actually gives us a cold signal, and it is cold relative to the trend, if that makes sense. So the trend is really positive, La Nina is cold, and so we don't have a signal there. Stated differently, next year, if we don't have another La Nina and it's neutral or even transition to weak El Nino, we would expect to see above normal temperatures forecast there because of the trend, if nothing else, right? So it helps provide stakeholders with that kind of information. You can dig into, if we really know what the ENSO impact here is and the official forecast deviates from that, you can now start to understand and communicate and attribute why. So some of that information you can get from the forecast discussion itself, which will provide that information from the CBC forecaster perspective, but you can help fill in those blanks, so to speak, for some of your local areas and local stakeholders. All right. Any questions? I see a hand raised. I'm not sure. That's a legacy hand from Chris, I think. So I'll put all hands down. All right. Any questions, comments? I hope you found this motivating a little bit about how we can use. And so, you know what? Let me do one thing, because Victor actually requested I do this. So we were all in climate impact space. If we go into correlation space, I don't know how well this works. We'll work here right now. And then we do this. I don't know if this is working in the current site. That's the problem.
Yeah, I don't, Steve, I don't think they ever got it
working. Okay.
fixed.
It works in the new site.
Okay.
Okay.
But then all it really does is just pull up the ezreal.
This site. Yes. That's what I wanted to show.
For PSL,
exactly.
yeah.
So it'll eventually link out to this site. So if you're not familiar with it, you'll see it in the new LCAT version. And what this allows you to do is get a better spatial view over climate divisions, but it also will let you do things with other variables. So, for instance, right now there's a very strong PDO signal in the North Pacific. What does that do? What you'll see here is, and I can do this real quick because I was just playing with this a little bit. If we do DJF and we do, 1950 to 2020, do PDO, we're going to do temperature for the time being, and we're going to lag it by index leads by 3 months. So we're going to look at September through November PDO, forecasting, so to speak, December to February temperature. What you see here is a pretty blah map, but there's a signal. And what you'll notice here is that this signal is pretty much ENSO but weaker. So maybe with a little bit of exception on the West Coast. But so you can use this to understand where you have some signals that are more aggregators of existing variability. PDO is really one of them in wintertime. But there's a lot of rich literature and developing science on PDO and AMO in the Atlantic, especially on multi-seasonal and decadal timescales and such. And that can be more fruitful. But you can use this on the interannual time period. You see that ENSO's not, the PDO is mostly capturing ENSO-based variability, or it's capturing atmospheric variability in the North Pacific that might not be predictable. So that's one of the things that you can see. So he asked me just to show this for precip. So we can surely do that. I predict it will look like ENSO. Am I wrong, Victor? No, it looks like ENSO. Perfect. So you see the local max here in Northern Rockies, Ohio Valley, and then the kind of little three-horned above along the southern tier. So anyway, but this whole analysis, it lets you look at all of that type of information with all of these different time series. The downside to it, this is one of the reasons I really like LCAT, is because in its compositing, LCAT gives you the statistical significance. It quantifies that for us, which is really nice. This site doesn't do that for the correlations. So when I see a 0.2 correlation, is that statistically significant? Well, it depends. It depends on how much data I'm looking at, and it depends on the autocorrelation of the data itself. So I have to, and basically it depends on how many degrees of freedom I have in the analysis. So it doesn't bake that in here. All that's baked in the composite side, which is why I really, really like it. So when you go to your stakeholders, if you're going to like in Miami and you're looking at ENSO, there's no doubt about that. That's what this means. If you're looking at Baltimore and Roanoke for like snowfall, say, yeah, all things equal, right? ENSO would favor less snowfall during meteorological winter in those areas. But as we saw, doesn't mean you can't get big snow events. We saw 95, 96 is a big outlier. And in a sample limited space, that's still important. So just kind of showing you how you can piece these things together. But yeah, this is a great site for correlation analysis that's spatial in nature. And then the really local analysis, really nice in LCAT. Okay. So I hope you found this motivating. We're going to do this again when we roll out the new beta version. So I know we have a couple minutes left. If there's any questions, happy to take any questions. I'll be posting the recording somewhere. We can send this out on some site that I'll send the email out so you can forward it to your colleagues, or you can watch it again and we'll go through a part that where I went through something fast or something. But I hope you got something out of this. I hope you found it useful. Again, go to the LCAT homepage, lcat.nws.no.gov. Register if you haven't. We'll prove it. You can go through the learning modules to get your bearings. Watch this little webinar to get motivated to how we can do this to communicate ENSO, trends, and other variability. One last little pitch, like I just said with ENSO and trends, things like that. If you were in the Mid-Atlantic, because I know it so well, you'll see that NAO and AO also have a strong ENSO, strong snowfall relationship. And so that's where a lot of the uncertainty comes from, right? So we have a nice ENSO signal. It's strong, but doesn't overwhelm everything. You can still get big snows in La Nina, and you can still have El Niños that don't have much snow. And where does that variability come from? Well, you can see that in the NAO-AO relationships. There's a strong relationship there, but we can't predict that for the whole winter with nearly the confidence that we can predict ENSO, for instance. And so that's where a lot of that uncertainty comes from, those big bars on the box plots. So those are all the types of things you can use to help your users understand what we know, what we can predict, what we know, but we can't really predict very well. And then there's always going to be, there's a residual that's just random because the atmosphere is chaotic, right? So, but we can help our users understand some of those different components of it as we go through. So, any questions? Thank you all for the engagement, the questions. Thanks for my staff, for our staff. They don't work for me. Our staff here at CSB for helping to be available to answer questions and jump in. Okay, and if you have questions, follow up with me, Jenna, Chelsea, anyone in our branch will be happy to help you navigate this. And do look forward to previewing the beta version of the new LCAT that's going to be launching in the next couple of years. Thanks, Brian. I'm hopeful that your users might find this interesting in Alaska, likewise other parts of the country. So thanks a lot. Thanks, Victor. I hope that everyone enjoyed this, and we'll be in touch. Don't be shy about questions. Always happy to help.